The Kepler Space Telescope is not only a dab hand at finding exoplanets, it's also revealing the secrets of the Seven Sisters. Also known as the Pleiades, this open star cluster made up of middle-aged Type E stars is visible to the naked eye, but has proved difficult to study. Now Kepler's instruments, combined with algorithms devised by a team of scientists from the Stellar Astrophysics Center at Aarhus University led by Dr. Tim White, are shedding new light on the variability of the companions of Artemis. Stars whose brightness fluctuates, or variable stars, are of interest to astronomers because they tell a great deal about their composition and the forces that power them. Some variable stars alter their energy output dramatically, becoming many times brighter over a span of the months or years. Others, like the Sun, vary only slightly, and this variability can only be measured by techniques like counting sunspots. Situated some 444 light-years away, the Pleiades, which, just to confuse things further, is also called M45, is of particular interest because aside from the 7 most visible stars, there are over 1,000 other objects present, including a collection of young, hot blue stars. The problem is that the variability of the major stars in the cluster is difficult to assess, as their variability is very short and the brightness of the stars gets in the way of making accurate measurements. It's the same problem that the Kepler Space Telescope encounters when it's hunting for planets. Exoplanets are very dim compared to the stars they orbit, so Kepler hasn't a hope of seeing them directly. Instead, it finds them by watching how the brightness of the parent star dips as the candidate planet passes in front of it. This use for relative brightness was right up the alley for White's team. The solution to observing bright stars with Kepler turned out to be rather simple, says White. We're chiefly concerned about relative, rather than absolute, changes in brightness. We can just measure these changes from nearby unsaturated pixels, and ignore the saturated areas altogether. Basically, what the team did was take the raw data collected by Kepler during its K2 mission and applied a new algorithm called halo photometry. This not only ignored the very bright light of the star in favor of relative changes, but it also weighted each pixel in the star's image to find the right balance and eliminate imperfections caused by the satellite's motion and other system problems. What they found out was that most of the 7 sisters had day-long periods, while the 7th star, Maya, rotates with a 10-day period, much longer than suspected. According to previous studies, this indicates unusual surface concentrations of elements like manganese. What we saw was that the brightness changes seen by Kepler go hand in hand with changes in the strength of manganese absorption in Maya's atmosphere, says Dr. Victoria Antosi, assistant professor at the Stellar Astrophysics Center, Aarhus University. We conclude that the variations are caused by a large chemical spot on the surface of the star, which comes in and out of view as the star rotates with the 10-day period. The team says that their research showed no signs of exoplanets revolving around any of the stars, but the new algorithm could help future survey missions to uncover planets around near, bright stars. If you like this video, please leave a like and subscribe.